In this video, we're going to be talking about ray diagrams with spherical mirrors and using those to describe some of the bizarre reflections, the bizarre images that curved mirrors can create. So here's our game plan with ray tracing. We're going to be drawing in a lot of representative light rays to get an idea of where the reflection of this candle is going to be in our spherical mirror. Some reminders: this is a spherical cross section here of what would be a completely spherical mirror, just part of it. And then the center of that circle is labeled capital C, and the point where parallel light rays focus is called the focal point, capital F. So I want you to consider a point source of light, like the flame on the candle there. Unlike the floodlight of the last video, these light rays, represented by the yellow arrows, they will not all leave that point source parallel to the principal axis. So not all of these light rays are actually going to go through the focal point, are not going to reflect back through the focal point. Some will, not all of them. There are actually infinitely many light rays to consider. I drew 5. It was going to take me too long to draw infinity. And so here's our game plan. How do we handle all of these light rays? We're going to draw three key rays of the infinitely many that are possible. These are called the principal rays for our diagram. Where those 3 rays meet, so too will every other one of the infinitely many light rays. And we'll look at some examples of that in class. So that point of convergence, the point where our 3 principal rays merge, that will be where the image of the candle or the reflection of the candle is shown. Now, for a plane mirror, the image was behind the mirror. That won't always be the case with these types of spherical mirrors because the light rays converge in front of the mirror. So here's our candle. Let's talk about the ray diagrams we're drawing. And I encourage you to color code your work. Of course, all of the light rays leaving this candle are going to have that orangish, yellowish flame color. But use a different color for each light ray that you draw, and that will help you keep your diagrams a little bit easier to read. So I'll be color coding. I encourage you to do the same. So the first of the 3 principal rays that we are going to draw. Now, this is just a representative ray of the infinitely many that are leaving. Well, the first one we should draw is the one ray that does leave the candle parallel to the principal axis. So this one right here. We should draw that one because we know what it does, right? It reflects through the focal point. That's what we talked about in the last video. So that ought to be one of our 3 principal rays. Principal ray number 2. Well, we could just run this geometry in reverse, right? If we look at the one light ray that goes through the focal point, it's going to reflect off of that mirror parallel to the principal axis. So there's the light ray that goes through the focal point. It's going to bounce off of our mirror to the principal axis. As you're drawing these, I encourage you to use a straight edge. Grab yourself a ruler, draw a straight line. Number 3, we should draw a light ray that passes through the center of the circle because we know that that's going to be along the normal line. And since it's along the normal line, it's going to reflect back the same way it came. And so those are 3 light rays. They all converge there. And it turns out that every single light ray from this candle that bounces off of our mirror is going to converge at that point. And so we get an image of our candle at that point of convergence. That's where our eyes would see the image of the candle. Most people call what you see in a mirror the reflection. The physics word we're going to use is image. So let's talk about how to describe that image. And the candle should be here. I guess it's faded out. But imagine, actually, let's go ahead and put that back in. Don't mind me. Animations, animation pane. I don't want you appearing like that. Save slideshow from current slide. All right, we're back at it, folks. Let's talk about how to describe this image. How do we talk about the reflection that was made by not just these three principal rays, but by all of the rays converging there? And we will talk about the lost art of image description. The lost art because that's the acronym we're going to use, LOST. So we want to talk about the location. We want to talk about the orientation. We want to talk about the size. And we want to talk about the type of the image. So location is where along the principal axis is our image. Well, our image is between the focal point, capital F, and the center of the spherical mirror, capital C. So location, that's words. It's a verbal description. It's between capital F and capital C. Orientation means, is my image upright or is it upside down, inverted? Since the image was formed on the other side of the principal axis, we had an inverted image. And so that is the orientation. It's upside down. It's inverted. Size, well, we can tell from this ray diagram, if we drew it to scale, that the size of this is smaller than the actual object, right? We would see a candle that is smaller. We'd see an image of a candle that is smaller than the actual candle itself. Last but not least, this is what we call a real image. And that distinction out of all of them is probably the one that students are least familiar with. So a real image is when the light rays really, or light rays actually converge. That's when the light rays actually meet. Whereas a virtual image, the light rays diverge and spread apart. That's what happened in a plane mirror. The light rays, when they reflected off of the plane mirror, didn't actually intersect. Our eyes traced back the rays to a fictional point of intersection. So that's what's happening in a virtual image. We'll do an example of a curved mirror with a virtual image also. And we'll talk about the implications of real versus virtual in the physical setting. So let's look at an example of diverging rays. So we still have a curved mirror. That curved mirror still has a focal point and a center, but now we've silvered the other side of this so that the reflection happens on this side of our curved mirror. And so it's still the same three principal rays. We're going to start with our first principal ray, which, again, color code your work. Our first principal ray is going to be the one that's parallel to the principal axis, leaving like that to the left. And it's still going to bounce off through a point through the focal length. However, it's not going to pass through, it's going to reflect. And so I need you to use your imagination with me for a minute and imagine a line that starts at the focal point and extends out to the point where our principal ray hits the mirror. The reflection happens along that line. So it's still the same idea, comes in parallel to the principal axis, reflects through the focal point, but it doesn't actually go through the focal point because the focal point is on the wrong side of the mirror. It just reflects along a line that the focal point is also on. All right, let's get rid of that trace for a bit now because that's not anything real. That's just there to help us visualize. Principal ray number 2 is the one that starts through the focal point and whose reflection is parallel to the principal axis. So same idea. I want you to imagine, if you will, a line between the source of our image, the flame, and the focal point. The light ray that's going along that line is going to stop at the mirror to bounce off, and we know that it's going to bounce off in such a way that it's parallel to the principal axis. And now we can go ahead and get rid of that fictional line. Number 3, we're going to be looking at the light ray that passes through the center of the circle, and it will reflect back in the same direction that it came from. And so, again, imagine a fictional line between our source and the center. The light ray that's traveling along that line is going to be reflected by the mirror, and it's going to bounce back in the same direction from which it came. Now, you'll notice that these 3 principal rays, and indeed every single light ray from the candle, diverges. It means that the red ray, the reflected red ray, the reflected yellow ray, and the reflected purple ray will never actually meet, right? They're spreading out. However, if your eyes were somewhere up here, you would see an image of the candle. Why would you see an image of the candle? Well, it's because your eyes would be able to trace back a point of fictional intersection. So what does that mean? That means that Hold on, my slides aren't progressing. Here we go. So these light rays don't converge, they diverge, but we can trace back the reflected rays to a point of convergence. So for the red ray, we can trace it backwards behind the mirror. The yellow ray, or sorry, the purple ray, we can trace the reflected purple ray behind the mirror. Same with the yellow ray. And what you get is a point where it looks like these lines intersect. That's where our image is going to form. Now, why is there an image there? It's because our eyes somewhere else don't know that these light rays are reflected. They just see straight line light rays. And so as far as our eyes are concerned, these light rays that bounced off the mirror all started at this point behind the mirror. So we would see the image of the candle behind the mirror, even though there's not an actual intersection of the light rays. So I like to think about this sort of like we've got these dumb monkey brains that evolved over time, right? And they think that that's where the light's coming from off of the mirror. They don't know any better. They can't tell that there was a bounce. And so that's where our brain thinks the reflected light rays are coming from. And so that's where we see an image. This is a virtual image. So we said there were real types and virtual types of image. This one is virtual. And the reason is there is no actual convergence of the light rays, but rather our brains just interpret a convergence by tracing the light rays back. So how would we describe this using the lost art of image description? The location for our image is between the mirror and the focal point, capital F, right? It lives in between those 2 points. And then orientation, size, and type are the other things we need to do. The orientation is upright. That intersection point is on the same side of the principal axis as our object, so it is upright, not inverted. The size is smaller. We can see clearly that the image is smaller than the object. And the type is virtual. The light rays spread out. We trace back a point of fictional convergence. All right, so that's how we would describe that image. Some vocabulary to finish us off. On the left, we have these curved mirrors that we saw. The converging mirror of our first example is also called a concave mirror. To help me remember that, I think about the fact that this mirror caves in, and so it's concave, caves in. And we have a convex mirror. That's the diverging mirror of our last example where the light rays spread out. I remember convex because it's the one that's not concave. So I've got a nice trick for concave. The mirror caves in, then convex is the other one where they spread out. So that's some vocabulary. You may hear me using those words. I will also use the words converging and diverging mirrors. So let's talk the physical difference between real and virtual images. I think I said we were done. We're not quite done yet. A real image can be projected onto a screen. And so this is a lens, not a mirror, but you can do the same thing with mirrors. We have a lens here and we have a candle. And the light rays from this candle spread out in all directions. Some of them pass through this lens. This is a converging lens, which we'll learn about later. But we can see that on this index card over here is an image of the candle. We've projected an image of the candle onto a screen. That's because the image is real. There is an actual convergence of light rays. Virtual images, such as the ones formed by your side view mirrors on your car, they can be seen by your eyes, but you're never going to project that image onto a screen because there is no actual intersection of the light rays. So your brain interprets that there was an intersection behind the mirror, but there isn't actually an intersection. Here's some labels for what I just said. The object was the candle, the lens was the mirror, and this real image formed because it was projected onto the screen. All right, so little speech bubbles to say what I said in words. All right, folks, that's it for this video. Ray diagrams for spherical mirrors. We'll do some practice in class. Hope you enjoyed.